Hello everyone, welcome to our first session for structural drafting. We will start with part 1 for structural steel design. The example we'll be using for the structural steel design is a warehouse structural design. The type of structure for a warehouse plays a comprehensive example of what we need for learning steel design, connections and all other components. Therefore we use this example for you. If we learn the software capabilities for creating this type of designs, that will allow you to do any other smaller designs easily. So this session purely just to introduce you before we start working with the software, just to introduce you what type of structure we're working with. As you would know, you guys doing the course for the undergraduate certificate, there's a small gap we need to fill here for the technical information comparing to the students are doing the associate's degree. Simply, the structure of a warehouse, the main feature about it is the large width comparing to its height. The opposite of the high-rise buildings, what we call it. This type of structures, they range from commercial, industrial, sometimes residential, very minor use for residential, but the main use for these structures are for commercial and industrial. You've seen them a lot around. If you notice, especially after this lecture, I'm sure you'll notice it later on, when you go around to most shopping centers, Bunnings warehouse, it doesn't have to have the warehouse in the name to be able to say this is a warehouse. Coles is a warehouse. Officeworks is a warehouse. Most of commercial buildings usually where we require large opening space, as you can see here, inside most shops we have larger opening space with minimum obstacles in the way. That's where we use this type of structures, where we use the capability of portal frames, what we call it, these large beams at the top. We call them portal frames, and these portal frames, these beams here, they provide us with the large space underneath. We will talk about the mechanism of this, which is very important for us. All what we're trying to do now is just an introduction. In terms of the use of these type of structures, we'll talk about the mechanism of this structure. How does it work together when we start doing the design? But before then, important parts that we need to cover. First of all, the use of these type of structures. As we agreed, a wide structure, not too high. This is the type of structures. We use them a lot in commercial, industrial type of structures. The cost of these projects, they range from $8 million all the way to $25–30 million. So they are considered to be part of the larger type of projects. So usually larger design offices and companies, they take care of this type of designs. Simply these structures, they form about 95% of most commercial and industrial structures, very commonly used. Okay. One of the other important points that we need to cover, the type of material. We have two main types of steel members. We should know this by now from basic drafting, and I think that you've got a small component in computing for engineering, that we have two main types of steel structures or steel members. One type we call it hot rolled structural members and cold form structural members. Hot rolled structural members are the larger, heavier type of structural members. When we talk about those, if you go to your Learn page, as we agreed, we have a design support documents section here. If we click on it, we go to hot rolled sections. Download the PDF and let's read through them. So those are produced by a major supplier here in Australia called One Steel is the main supplier, and we've got slightly different grades, 300 and 350 mainly for the hot rolled structure, for the hot rolled members. Now in terms of shapes, when we say, just before we move on, when I'm saying 300 or 350 grade, that's the yield capacity of the steel. See, we've got here, these are considered to be 300, and that's the grade for it, 300 plus we call it, which is 300 grade. you see the capacity, the yield stress or the yield strength for that material. It's close to 300 MPa, megapascals. And we've got the higher grade steel, which is 350 MPa steel, and that's where the yield capacity is above 350 megapascals. Okay, so these are the two main steel grades in terms of the material, the strength of material. Put that to the side. The important part for us here to understand the section of each member. So we've got different type of sections, and based on these shapes we use them in different applications. One of those commonly used sections are welded beams. So welded beams, it's simply a group of plates, as you can see them here, group of plates welded together to shape this section for a member, and this member will be called welded beam. There are specific sizes, thicknesses, lengths and grade of material welded together with specific type of weld and strength, and that will form what we call them welded beams for certain sizes. We've got them, they range between, there we go, they range between 700 welded beam all the way to 1200. Those sizes, we use them when the standard beam members, what we call them universal beams, they're not large enough. Because the largest section in the universal beams, if I scroll down to universal beams, the largest section we have is 610 millimeters. That means the depth of that, if you look at D, for that is 612 millimeters maximum. If we need a stronger beam, and these beams they can't do the job, that's where we start using the welded beams. Anyhow, we will not be using welded beams in our project or welded columns. Let's focus on the universal sections. Universal sections, that means all of these hot rolled members. Hot rolled members, please, if you don't know the difference between hot rolled and cold formed type of steel, spend the time and Google it to know the difference. Try to go to Google and maybe watch some YouTube videos on hot rolled versus cold form. So the two type of steel, we've got the hot rolled type of steel and cold form members. Hot roll, usually they have to heat the steel to a point where it's melting, it's red hot, so they can form into shape. Cold formed steel, they use thin plates and they bend these plates to shape the structural members, and that's why we call it cold form. They form it while it's cold without heating. Maybe it's important information for you to search this type of material or the difference between them. Going back to our members, in terms of the shapes, universal beams are known to be narrow and deep. When we say deep, you see that value D, that's usually referring to the depth. B for the breadth. Okay, so they are usually narrow and deep. Comparing to very similar shape, we call it universal columns. If I scroll down, which is different, it's short and wide, exactly the same shape but different ratios and different weights, obviously. So the main difference we call these shapes universal columns and these shapes universal beams. Now universal beams are deep and narrow because usually we apply the load in this direction. So we need them to be deep in this dimension here to resist this load, and we will see in our design. If I show you our design, what we're trying to design, for example, I've got this rafter here. This is made of a universal beam. So let me just look at this frame. Only. Okay. So if I look at this frame, at this beam here, as you can see, it's deep in this direction, but narrow in that direction, in the width. It's not very wide, okay? Why? Because mainly the main load we are expecting, or the main weight, let's put it this way, as a simple way of saying load, the main direction the load will be applied on this frame is downward here in terms of weight, the roof weight, if there's any people working on site, if we have any solar panels, if there is any wind pressure, which is one of the major loads we have here, will be either pushing down or pushing up, applying negative pressure. In these cases, regardless, the application of the load will be applied in this direction here. So downward or upward. So we need this member mainly to be strong to resist this movement, okay? Not to bend either downward or upward. Therefore, we need them to be deep and not too wide. We don't need them to be wide. If we have them too wide, that means we'll have too much of material for no reason. In fact, that will add weight, and that will make our problem even worse. So that will add more weight, has to be carried by this member here for a long distance. You will see now when we start talking about the design, the length of this member, it's about 15 meters. So this is universal beams. Universal beams are mainly to resist forces applied in this direction. Okay, so if I draw here, so this is the direction we are expecting the load to be applied. Okay. Now in terms of columns, that's the same shape, universal beams. In terms of columns, the difference here, we don't expect the load to be applied this direction here. We expect the load, so I'll show you if I draw here. The difference now, universal columns, instead of being universal beams, the type of load or the direction of the load application usually comes rather than from the side. For columns, usually the load will be applied from the top here. So on this surface here, that's where the load will be applied. So that's why we use them for columns. In this application here, if you can look at this shape here, we're not looking for the load to be applied on from the top flange, what we call it. I'll go back in a minute and go back through the components there. What we're looking for the load to be applied on the entire cross section here. And that's why we use, it's more used for columns. So it doesn't mean that we only use it for columns. It doesn't mean that anything with columns we have to use this shape. It doesn't mean that we can't use it for beams. All is possible, but what we're trying to say here, that it's more used for columns. That's why we call them universal columns. Okay. Now, in terms of the components for each one of those, it's important to notice or to note that this part here, we call it the flange always. Okay. These are the two flanges, the top, for example, here, and the bottom, and the same will apply for the universal beam. So the top plates here, we call them flanges. Okay. These are the flanges details. The flange. Okay. The plate that connects between them, that's the whip plate. Okay, so that's your whip plate. And we've got all the specification for the flange, the width, the thickness, and the whip plate thickness and material and strength, all of those in these tables. Okay. Also, important for us to learn how to read these names. Our end goal, guys, just to keep in mind, let me show you what we're trying to achieve at the end and what steps we have to go through to produce that. This is our end goal. We need to design this structure. We need to understand every single component in this structure. We need to know the name for each one of those. We have to speak the same language. When I'm saying girds, straight away I'm referring to these members here on the sides. Okay. When I say purlins, it's the same members but at the top for the roof. These few members, I'll talk to you about them in details in a minute. We've got the wall pricing, we call it vertical cross pricing. We've got similar pricing in the roof, we call them roof pricing. Obviously we've got columns, rafters, and the foundation. we've got too many components. We have to understand the basic job for each one of those so we can design it correctly. We have to know the name for each one of those. So when the objective of our exercise, when we see a plan like this, we have to understand every single component here. What does it refer to? The S referring for struts, the FB for fly brace. Even if I'm just brushing over them quickly now, we will go back in details to talk about them later on. Okay, so don't stress out about those. I'm just trying to lay the foundation for what our expectations should be at the end of this course, or at the end of the steel design of this course. This will teach you the main job for each one of these components. Will teach you how to use the software to model them and connect them, because the software can do anything you ask the software to do. You have to have the right knowledge to provide the right information. So you have to have the right knowledge. For example, let's go back to Revit, to know what type of connection I need to have here, what type of bolts I need to have here. Why do I have to have this small bracket here? We'll call it haunch. Why do I have to have one of those in the center? So the software can draw exactly these two rafters for you, the two beams, without that haunch. I can just get rid of that altogether. It's your job to give the software the right instructions, and we need to understand what are the right instructions. Okay? Let's stick with the naming for a minute, for now. In terms of the naming, going back to this file here. So I'm asking all of you please to download this file. You've got them on your Learn page. You need to read through them and try to understand every single component. If you have any issues with any of those, I highly encourage you all to Google it, search it, research it. The most important part we can teach you in this course and in engineering, how to research things. It's not enough for you just to wait to take all the information from one person. It's very important for you to learn how to search. Your searching will be your tool number one in your improvement for the future, even during your employment. Okay, so the main components, steel components, we've got universal beams, universal columns, we've got the tapered flange beams. We don't use those a lot. Okay, so not as much as universal beams and universal columns. It's exactly the same as the universal beams. What we got, as you can see, the flanges are tapered a little bit to the edges. Okay, so they're not really used a lot. PFCs, parallel flange channel, we refer to it as PFC. It's very commonly used, okay, in too many applications, the PFC members. So we have to understand what I'm saying. PFC refers to parallel flange channel. This channel, please note, this channel is different than what we'll be talking about in a minute, a C-section. This is not a C-section. What we call it C. This is a cold form, thin. Look how thin that member is comparing to this PFC. Okay? Complete two different members. We have to keep an eye on that. We've got universal bearing piles. Those are used mainly for foundations, so again not very important to us, but if you see UBP, that means it's universal bearing piles. Okay, so you know that. Now, very commonly used, EAs, or equal angles. That means we have an angle, it's equal in both direction, or what we call them, the two leaves are equal, or the two legs are equal, all commonly used. Okay, so obviously all these components, all the properties are shown here in terms of measurements for each one of those. You don't need them too much, they're all stored in the software, but we need to understand when I'm saying we need to use 75 by 75 by 5 EA for bracing. The minute I said EA, that refers to equal angle. 75 by 75 by 5 refers to 75 millimeter in this direction and 75 millimeter that direction and 5 millimeter thickness. This is the standard. Okay, so if I look here, I've got 75 by 75 by 5 by 6, 8 and 10. Okay. Now, similar to the EA, we've got something slightly different member. We call them UEA, unequal angle, or UA. Both are used. Sometimes we call them UEA, unequal angle, or UA, unequal angle. Okay? Exactly the same thing. The only difference here, we've got one of the legs here, or one of the leaves is not equal to the other. That's why we have to specify both of them. Sometimes, just to go back to the equal angles, we say 75 by 8 EA. That means it's an equal angle, 75 on the outside, 8 millimeter thick. Whereas for unequal angle, I have to specify both measurements. I say 75 by 50 by 5. For example, I don't think we have that. We've got that. 75 by 50 by 5. Unequal angle. We have to be careful. We have to know how to read them. Got all of those. And the rails, those mainly are used as rails. So we're really not going to use them too much into our structural design. What I need you to focus on, please, unequal angles, equal angles, PFCs, UCs and UBs. Okay, so the universal columns, universal beams, parallel flange channels, and equal angles, unequal angles. Let's try to read the naming code for each one of them. That's important. I'm sure you've learned it before, but let's make sure that we remember. So when I'm saying 610 UB125, the first three numbers straight away referring to the size. As we agreed, the important size for us is the depth, how deep that is. That's 600, what we call them nominal. Very important to learn this word. When we say nominal 600, that means it could be 60, look at it here, 607, 602, 612, around 610. Okay, this is what referring to as nominal. UB refers to universal beams, and 125, very important to know, this is the weight per linear meter. In other words, if I go back here and I cut 1 linear meter sample of this beam, that will be 125 kilograms in weight. So it's important for us to specify the weight per 1 linear meter, and then by knowing the entire length of our member, we'll be able to know the entire weight. That's for universal beams. The same thing will apply for universal columns. Okay, that will give us the size, nominal size, again 310, could be 327, could be 308. So it's around 310. UC, that means it's universal columns, 158 kilograms per linear meter. By the way, for example, 200 UC 52. We don't say usually 200 UC 52.2. So we usually say 200 UC 52. It's known to be that. Okay? Even for example here 100 UC 100 UC 15. Doesn't have to be 14.8, 15. That's normal. Okay? Or 14. That's fine. It's only one member. Okay. As we agreed, the same thing will apply for universal columns. Now moving on to PFCs, the only one number we're showing there is the size of the channel. Okay, because when we have one channel with one size, we have one weight for it. Okay, and we get the weight here, so we don't use the weight usually as part of the name for the channels, only for the parallel flange channels. So the parallel flange channels, we usually just specify the size. That means this is a 380 deep. The depth is the important parameter for us. That's 380 millimeter deep parallel flange channel. Angles, we said we spoke about the name code for the angles. So for equal angles, we could just say 200 by 26 EA. That means it's 200 this way, 200 that way. Obviously on the outside, please look at it. That B1 value is reading on the outside of the channel. That's 200 millimeter by 200 millimeter by 26 millimeter thick. That's a very thick channel. Okay. If we're using, so we can use here, we can say the longer name, or we can say 200 by 26 equal angle, EA. But for the unequal angle, it's important to specify the two sides, 150 by 100 by 12, UA, or UEA. The same, it's unequal angle. Alright then, I'm not going to spend too much time with it, guys. Just please make sure that you spend time to read through them, and you know, because we'll use them a lot down the track, okay? That's for hot rolled. As we agreed, all of those members, we call them hot rolled members. That means they have to be heated to a red hot temperature, so they are malleable, they are softer material, so they can form them into this shape. Okay, they can't form them, they can't create this shape without heating the material. Now the second type of material that it's very commonly used for usually smaller capacity or slightly weaker members, we call them cold formed. There's a name, so cold formed steel, okay? Or sometimes we call them rolled form steel or rolled form steel. Let me check here, rolled, if you can find anything there. So the other common name for them is rolled form steel. Okay? Why they got this name? Because that's how we form them, using roll formers.
This is a Dalarna University production.
Roll stands that change the sheet's shape. The sheet undergoes what is called a profile bending.
Okay.
Roll form detail.
Again, as I mentioned before, I highly recommend that all of you guys, anything that you're wondering about, I could be saying that you don't know exactly, please spend some time to try to Google it or look it up for some time until we get the right foundation. Okay, the right structural knowledge, and then we can start be more confident about those. This is when we were talking about the hot rolled steel, so that's where they have to heat the steel so they can form it. Okay, right, going back here. So these are very commonly used to, usually are used as secondary members. When I'm saying secondary members, let's go back to our frame here. If I go back to here, showing you the entire structure. This is the main structural components, and all of those we use, most of them are hot rolled steel, thick steel. As you noticed now, since I was describing this material here, the hot rolled, it's all larger thicknesses, 12 millimeters, 16, so they are thick material usually, okay? That's why they've got that extra strength into the members. But now, as on the outside, or the shell on the outside, for after we create the main structure, this is our main structure, this is what is really doing the actual support for them. This is what giving it the strength for the structure. But on the outside, let me just show you, we've got some components there, we've got them hidden. There we go. So we can create the secondary structure on the outside, so we can put sheets, the walls, roof, all of that. We need to use slightly thinner material, not as thick as the main structure, and that's where we use the cold form steel. Okay, so all of those are made of C sections. as you can see, the thickness for that material is not very large. Okay, so when we need to use those, let's go back here. Got the second document located exactly the same. If you go to your design support documents, we've got the second thing called LISAT Z and Cs. Now, LISAT is the company, the main manufacturer. This is the name of it. LISAT is the main manufacturer, the largest manufacturer, part of BlueScope, what they call them, the group of companies, are the main manufacturer for those. Z and Cs, Purlins and Gertz. Purlins and Gertz, we will talk about that. That's the name we will use as an application. Z and C is just for the shape. Simply, if you look at the two components that we'll be dealing with, are they going to be, I'll show you this in 3D, are they going to be a Z shape like that, or a C section? Okay, so we'll call them Z section or C sections. In our design, we will use the C section. Again, for their name, they've got their name codes, slightly different name code than what we had before. Z or C, you can't use Z and C. They're saying here Z or C, depends on the shape. Now, let's choose, for example, the C. C110. That means it's 100 millimeter deep, nominal. Please keep an eye. We love to keep things in engineering. Unfortunately, we keep things, we call it nominal. We don't like to be restricted to very precise numbers. So, we call it nominal 100 millimeter deep. 10, it's 1 millimeter thick. Okay? The thickness here, it's BMT, what we call it, the BMT. Let me check where I can find the BMT for you, so you learned that one too. Control F, BMT. So, when you see BMT here, refers to the base metal thickness. Why is it base metal thickness? Because this particular type of steel, because it's very thin, we have to protect it against corrosion. If you noticed so far, you always seen it silver color shiny. If you noticed here, in most of these photos that we've been looking at, you see it always in silver color and shiny. That silver color, shiny silver color, it's zinc. Okay, so they dip it into zinc to give it that coating to protect it against corrosion. Therefore, that will add some thickness. And for us to know the exact thickness of material that gives us the strength, we call it the BMT, the base metal thickness. Okay, so it's not the all BMT millimeters. It could be, if you measure it, you'll find it slightly above more than 1.2 millimeters. It could be 1.3 or something, because usually we add 0.45 or 0.7 of millimeter for the zinc coating. Anyways, the important part for us, when we read this name code, we understand. We don't need to memorize. That's the point we're trying to make. We're not asking you to memorize, if I choose this section, what would be the width, what would be this, what would be that. All I'm asking you, if you read this name, you need to understand what does it mean. And that will be part of your quiz, could be part of your exam, could be part of anything we may do as an assessment down the track for these sections, as well as the hot rolled sections. So, if I look at this, for example, C25019, that means it's a C section, 250 millimeter thick or about. Well, for me, nominal, we usually say nominal 250 millimeter thick and 1.9 millimeter, 250 millimeter deep and 1.9 millimeter thick for the material. Okay? There we go. That's all the members here, the values. We need to keep that in mind, please, okay? Now, since we know these sections, I'm assuming that you should know them by now. Please, you should learn and memorize how to read these sections. Let's move on to our next point here. So we talked about the hot roll structure, members and cold form members. We will talk about in more details later on, as we use them during the design on Revit we will talk about more specifications and details of them. That will lead us now to the important part of our warehouse structure. Of our introduction, which is the components of a warehouse structure. I'll start that on the video after this one. Let's stop our video here. We'll start on the next video to talk about the main components, so you can come back and review it later on.